There is no any new subject today, and today is the last lecture, you know. I will solve some problems. And there was one problem I remember in the dynamical subject of rotational motion. If you remember, there was this problem of a mass attached to a pulley. And remember, we had these two rods having different configuration attached to the pulley. And as the mass M falls down, the pulley and these two masses, they are connected with a rod, rotate together. We have two cases. In the second case, these two masses are the same, but they are closer to the center of the pulley. And the question was, if you release two masses, the hanging masses, from the same height and from rest, which one lands first? Right? This was the question, if you remember. So, to attack this problem, in fact, again, you have to think the Newton's second law for both the hanging mass and the rotational pulley. So we have to write down two equations to get any idea of which one lands first. Is it helpful to find the acceleration for both cases? If you find, because they are from rest, they are accelerating from rest, and they both have the initial velocity 0. And if, of course, you release it, the system will have some acceleration because there are forces and there are masses. And the force that causes the acceleration, of course, will be gravity on the small mass. But if there is no any mass attached to the pulley, will there be a rotation with this configuration or this one? Imagine there is no hanging mass. If you release the system like this, will you have any rotation? The pulley, yes, the stick and the pulley. The stick, these two masses are attached to the pulley. When the pulley rotates, all the system rotates altogether. If you release, imagine there is no any mass attached to this. If you release this system, will the pulley rotate? Well, I guess it will not rotate, right? Because if you ask this type of question, what you should seek first, whether you have a net torque on the system. And this torque, since the system will rotate through this center, right? The torque has to be calculated with this center. And if there are any forces acting on this pulley and the stick system, there must be some linear forces, like we have linear forces on this side, down, and on this side. But if you ask this question, if the torque provided by these two forces on these two attached masses on the stick will rotate the pulley? No, because they will provide the same torque, but in opposite directions, right? So if you release the system, since the system is in equilibrium, there will be no rotation. Only if you attach a mass, like there is a tensional force, an external tensional force, then in that case, the pulley will rotate. Anyway, as I said, to get an idea of how which one lands first, it is enough to calculate the accelerations and compare the accelerations themselves, A1 and A2. So when you release the system, what will happen? This rotating system will rotate with an angular acceleration alpha 1, and the small mass, hanging mass, will go down with acceleration A1. But we know that A1 and alpha 1 are related to each other, right? What is the relation? Yes, alpha 1 is equal to A1 divided by R. I assume that you know this, okay? Because we already discussed this many times. Okay? If there is there's confusion on that, just go back to your lecture notes and understand it. Anyway, so with this relation, with this help, that I will be able to calculate the acceleration of the system for both the hanging mass and the rotational mass, and then I will compare these two at the end. But again, before we start solving the problem, what is the difference between these two systems? What? Radius. Well, I think what you're trying to say is the difference is about this rotational body. The pulleys are the same for both, but the thing is, this stick attached to the pulley, on the first case, these small masses are far away from the center, but in the second case, they are closer to the center. So, what makes which quantity then will be differing for these both cases? If you think their moment of inertia, right? This system altogether, the stick and the pulley, have some moment of inertia because they are rotating all together. We know what the moment of inertia of the disk. For both cases, the moment of inertia of the disk is the same. But if you think this system, these masses, and if any mass, point mass, is rotating around an axis, which has a distance r to the center, this has a moment of inertia mr squared. Right? We know this. But the thing is, these masses in the first case are away from the center, but in the second case are closer to the center. So mr squared for this and this case, the first case is larger. So the contribution coming from this rod and the stick and the masses attached to it to the moment of inertia is larger than in the second case, right? So the moment of inertia I1 of whole rotating system in the first case is larger than the moment of inertia in the second case. So this is something we know before we start. But the rest, you will see, principally will be the same. So the first thing is, you just write down, choose first of all the directional signs. Downward I choose as plus. This is again important. Last time, the people who were in the lecture in the last time, remember this. If you choose this plus sign for the hanging mass, you have to choose the clockwise rotation of the pulley as plus. This is very important. Okay, you have to be consistent with the directions of the rotating body and the directions of the linear body. The motion of the direction of the linear body. So once we fix these, also the directions, we are ready to solve the problem, to write down the equations of motion. The first thing is you write down the equation of motion for the linear mass. Okay, this is just a convention. It's up to you. So for the linear mass, for the first one, since it is going down and the plus direction is down, the first force is mg, right, minus t1, because t1 is in the opposite direction. This will be equal to m times a1, right? M times a1. This is the first equation for the hanging mass. For the same system, also I have to write down the torque equation for the rotating part, right? And the total torque for this disc attached to the stick is T1 times R, right? There is no any other force that can provide torque to this pulley system, right?
What about the mass?
Well, as I said, the weight of this part, because these balls are equivalent to each other, they are identical. The weight of this one will, yes, provide a torque, but this one also will provide the same torque, but in the opposite direction. So I'm not including these two torques. This is why I explained before that otherwise I have to include this, but their sum is equal to 0. Anyway, okay? So T1 times R will be equal to the total moment of inertia of this rotating system, okay? The pulley and the stick, right? I1 is this moment of inertia, and I1 times alpha 1. But as I said, alpha 1 is related to A1 by A1 divided by R. So we have the second equation, and from these two equations, I can easily find A1, the linear acceleration, in terms of the masses and the moment of inertia. And the rest is just algebra that I hope you can do it, and I'm just writing the result. So the result is, as you see, A1 in terms of G and the mass and the moment of inertia is G mr squared divided by I1 plus mr squared, where this m in here, the small m, is the mass of the hanging mass, okay? So don't mix the mass of the rotating system. The mass of the rotating system is included in I1. That's, right? But I don't have to express the mass of the rotating system explicitly because I1 has this information. But one thing I know that I1 is larger than I2, right? That information will be enough for us. Anyway, A1 is this. If you solve for A2 for this problem, everything is the same, right? What you see is everything is the same. The only thing different is just the moment of inertia. Instead of I1 in here, in this equation, you will put just I2. That's it. So A2 will be, again, this similar kind of expression, but the only difference is in I1. So instead of I1, I put I2 in here. Now you are ready to compare A1 and A2, right? If I1 is larger than I2, being everything is the same, rest, A2 will be larger. So A2 will be larger than, I put this order in here, A2 will be larger, so that means T1 will be larger or T2 will be less than the one on the right side lands first, right? So T2 is less, and if you release the system from rest for both at the same time, then the right hanging mass will land first. Anything unclear or any questions on this? Okay. All right. This was the problem from 2 lectures earlier. And remember, I asked you to find it anyway. So next, I have chosen some problems from your textbook and also from quiz. Let me concentrate on this one. This we have discussed last time, remember? It's another version. I like this kind of questions because it's somewhat confusing for you. And we have, again, a spool, a disc. Around the disc wrapped a string, and the string is pulled by this force F. And we have the mass of the disc, and the radius is given. The question is, what is the acceleration of the center of mass is given by 4 times the force F divided by 3 times the mass M. We have to show this. Okay, in the first part. Well, the disk has the moment of inertia, right? And we know I is equal to 1/2 m r squared. So the ones who were in the lecture last time. So what do we start with? The only condition is that the disk is rolling on the surface without slipping. There is friction, of course. Okay? There is no slipping. Okay? It is rolling without slipping. So, how can you attack the problem? We have friction. We have friction. It is rolling without slipping. Kaymadan yuvarlanıyor. Kayma yok in Turkish. Yes. So, before you start writing down the equation of motion for the Newton's second law, as your friend suggests, you have to show all the forces acting on the disk, and this includes, of course, the friction between the disk and the surface. In the picture, it is not shown, of course. And also, we have the applied force F. So, I say that the frictional force between the disk and the surface is to the right. And let's write this as Fs. Okay. And you might ask, why did you choose the right side, the right direction as the direction of the frictional force?
Why?
Well, you can ask yourself, if there were no friction between the disk and the surface, when you pull the spool, it will rotate, right, in the clockwise direction, right? It will slide. But if there is a direction, the friction, then the friction will act in such a way that it will oppose to the direction of rotation, right? And this is the only case if you have the frictional force to the right, okay? If you know what I'm saying, when there is no friction, the disk will rotate to the right, but since there is a friction, friction is always opposing to the motion, and the friction will try to rotate in the opposite direction. So that's why we have to put the. But it doesn't matter. It doesn't have to be any. You don't have to be right in assuming the direction for the frictional force. Try it yourself at home. If you had chosen this direction as the frictional force and formulate all the equations of motion, you will find the same answer. Okay? This is, I know, confusing for you, and I will explain this after the lecture for the ones who are curious about this. But for the time being, I have to continue because we have a limited time. So let's then, putting these forces, the force F to the right, I'm dropping the vector signs, plus the frictional force, and this will be equal to, because I'm writing the Newton's second law for the center of mass only. Okay, so this will be m times the acceleration a. So the question is, what is the acceleration? Okay, so we have to find the acceleration a. But from this only, you're not able to find the acceleration in terms of the applied force, but there is frictional force. We need a second equation. The second equation will be the torque, right? Because there is a rotation. So the rotation, you have to take which direction as plus, because I am taking this direction as plus for the center of mass. If you choose this direction as plus, the clockwise direction must be taken as plus to be consistent with the motion. Okay? To be consistent with alpha and a, because we have alpha and we have also a. Since alpha and a must be the same sign, I have to put this condition. So, and also you can put alpha equal to a divided by r. There is this relation always. So we are ready to write down with this choice of sign the torque equation because we have two forces, and the force F is trying to rotate the disk in the plus direction with this choice, right? With this choice. So I have to put the torque contribution coming from F times R. What about the contribution coming from the friction for the torque? Since F will try to rotate in the opposite direction, in the negative direction, right? I have to put a minus sign. Small f times r. And this will be equal to the moment of inertia. This time I will write the moment of inertia explicitly in terms of masses and the radius. And alpha divided by, alpha, and alpha is A divided by R, right? So I can work it out. And these R's, this one and this one, right, will cancel all. And I can express the frictional force in terms of the applied force. And the frictional force, in that case, on the right-hand side, I have only 1/2 m times A, right? And F minus, if I'm not wrong, just correct me if I'm wrong, it will be F1 minus 1/2 m times A. So if you put this in the first equation, right, 2F, right, because I have to add this to the F, and then minus, we have minus 1/2 MA, and on the other side we have M times A, right? So we have 2F is equal to, on the right hand side I will have 3 divided by 2 M times A, and if you solve for A will be equal to 4F divided by 3M. So this is the expression for the acceleration of the rolling disk in terms of the applied force and the total mass of the disk. All right, this is easier than yesterday. Tuesday. Because
Why do we take minus F?
why do we take this minus sign?
Yes.
This equation on the left hand side, this is the net torque, right? This is the net torque. And I'm just writing the sum of the torque for this rotation. And as I said, the torque provided by the applied force F is plus, because this F is trying to rotate the disk in this direction, in the clockwise direction, and I already chosen this direction as plus. And the torque is just F times the perpendicular distance to the rotational axis, F times R. But this F, this small f, or the frictional force, if you just pause the picture and just see it, nothing else you see, just this frictional force, F, it will try to rotate the disk on the other direction, right? On the negative direction, in the clockwise direction, which is opposing to this direction. That's why I take minus. The rest is the force of the friction is to the right. You have to find anyway, and it is equal in magnitude to F divided by 3. So from these equations, it is very easy. Just you will put this this A, the solution, to here, and you will find the F, the frictional force, as 1/3 of the applied force. This is always true. If you have a disk, if you pull it with an applied force, the frictional force is always 1/3 of your applied force. As long as your disk is not sliding, it is rolling without sliding, okay? This is true always. Whatever the force you apply, the frictional force will depend on the applied force, and it will always be 1/3 of the applied force. So the rest is, well, if the cylinder starts from rest and rolls without slipping, what is the speed of its center of mass after it has rolled a distance of d?
Acaba neden hani F'i 3'ten çekiyoruz ya, onu 2'ye almamız gerekmez mi acaba?
If you think that the rotation is taking place around this point, the contact point, then you're right. Then in that case, you will choose, right? This is the second way to solve the problem, as you suggest. If you think, this is another picture, if you think that the disk is rotating around this contact point, then this will be even more easier to solve. Okay, I have to include this F in here, and I take this rotation around this axis to find also the F. But when you think that this force will rotate the disk around the point of contact, then in that case, your torque equation, you have only one equation, torque, F times 2R will be equal to the moment of inertia around this point. In that case, the moment of inertia will be different. I will explain to you, okay, after the class, because I have limited time. There is another way of solving this, and it will be more easier, but in that case, you will not be able to find the frictional force.
But there is mg.
Well, there is mg, but the mg does not contribute to the rotation, right? For this case, or for both cases anyway, mg is from here, right? And mg, the force, weight, has no distance to the rotational point, rotation axis. So this has no contribution to the rotation. The weight of the disk will not contribute to its rotation. However you choose a big disk or a small disk, the rotation will be affected only by the frictional force and the applied force, not by its weight. The third part of this question is related with the kinematics, linear motion, and it is related with your earlier chapters. What kind of motion does the center of mass having in this problem? Is it a constant velocity motion or a constant accelerated motion? It's a constant accelerated motion, right? We already defined the acceleration, and this is the 4f divided by 3m is the acceleration of the center of mass. So the third part concerns about this acceleration, because it is asked to find the velocity, and we know how to find the velocity in the case of constant accelerated motions, right? If you are given a distance, the time is not included, but since we know that the velocity is always related to the acceleration, v is equal to a times t, but we don't know time, what time is. The only given thing is d. It rolls a distance of d. So I have to use another equation. Remember, I had this v square equation is equal to the initial velocity plus 2 times the acceleration times distance t. So you'll use this equation to find the center of mass velocity after it rolls a distance d. A, because it asks the velocity of the center of mass. Okay, the speed of the center of mass. But if it asks the angular velocity, it is not a difficult thing for you to calculate, because v and omega, the angular velocity, are related to each other, and omega in fact is equal to v divided by r, right? Once you find v, it's one step away to find omega. So you can find this v for yourself anyway. Yes.
Center of mass dediği şey, speed of center of mass burada W mu yoksa normal V mi?
V. The speed of this point, the center. Because the center of mass is just right in the geometrical center of the disk. Okay. Not what? But you know that the speed of the point on top of the disk will be, remember, twice. And the speed of the point in contact will be always equal to 0. Even the disk is moving, this point has 0 velocity, 0 speed all the time, as long as the disk is not slipping. Okay? Any questions about this problem?
So omega is also theta over r. Angular.
Omega is V over R.
And also theta over r.
No. The definition for omega, if you think that the disk is rotating an angle, okay, because when it's rotating, its radius is swapping a angular displacement. Then in that case, omega is d theta over dt. It is angular velocity by the definition. It's the speed of changing of the angle, right, in time. And what is alpha? Second time derivative of theta. These are the definitions. Okay. So let's think about another problem. This problem is also interesting. Again, from your textbook, you have this yo-yo. This is called yo-yo, right? And we have a disc, and attached to disc to the rim a string. When you pull this, yo-yo will go in other directions, and you apply a tension in the string. And the thing is, this yo-yo is just hanged on the ceiling or a bar, whatever the fixed point, and just you release the disc from rest. The question is, what is the tension in the string? It says the tension in the string is 1/3 of the weight of the disc. You have to show this. So the tension T on the right hand side, I have pictured the problem's free body diagram. This T, it says, will be 1/3 of mg. So you have to show this. Again, to attack these type of problems, always, if there is rotation, rolling, and motion of the center of mass, whatever, you have to start with this free body diagram. You have to find all the forces acting on the body, and also you have to choose some directions, plus directions. Okay, you have to choose this, because to put a relation between alpha and A. To find tensions, accelerations, frictional forces, whatever, to find these quantities, you have to solve the Newton's second law for both the rotational motion and the linear motion. So the one I have chosen for the plus rotation is, when the disk falls down, it will rotate in the clockwise direction. Again, I choose the clockwise direction as plus. In that case, the motion of the center of mass is down if it is rotating in the clockwise direction, and I choose downward direction as plus for the linear motions. So once you set these choices, you are free to go to put the equations. And of course, there is this always relation between alpha and A. Alpha is equal to A divided by R. So if you think the linear motion only, the linear forces, sum of all linear forces must be equal to m times A. So the force mg is down, and since the downward direction is plus, I take mg as plus. With this choice of coordinate system, the direction t will be up, and it is minus. So I have to put t as minus, and then this will be equal to m times A. The rest is the second equation for the torque. And the torque is T times R. Well, T times R is plus, but I have chosen with this choice, I put minus t in the previous equation. Why we have to put plus tr? Because tr is the torque, and the torque provided by t is rotating in the plus direction. So I think this will clarify your previous also question. Then what about if you think the rotation around the center of mass of the disk, is there any contribution to the torque? No, because the mass, the weight, is right at the center, so there is no distance to the center. mg times r is 0, so the torque contribution coming from the weight is 0. We only have tr, oops, sorry. Okay, we only have one component for the torque, and this is tr, and this is equal to always I times alpha, the moment of inertia, and I replace alpha here by a, because I have to solve t and a. And the next thing is I have to combine these two things together, right? 1 and 2, equation 1 in here and 2. If you combine this, you can get an expression including only a. Okay, so a is equal to, from this, remember this is the same expression that I have solved the first question, this rotating system, and there is a tension that rotates the system, the tension and force. This is the same expression, nothing else. So, but of course the only thing is I here will be replaced by 1/2 mr square, because this thing is a disk. And if you also put this, well, you can always find t in terms of ma and moment of inertia once you put this a, the solution of this a, this term, into the first equation. Okay, here you can express t in terms of the moment of inertia g, m, and r square. So once you put this, you can express t, so t force after simplifications, if you also put I is equal to 1/2 mr square, the explicit expression for I, and you will find t as 1/3 of mg. Well, I guess you have followed this, right? Is there any missing point? This is, there was this one question, the previous question, rolling disk on the surface. What was the friction in terms of the applied force? The result was always 1/3 of the applied force, right? And you see here, applied force is just the weight of the disk, and what you find is not surprising for you. T is just 1/3 of the weight.
If you apply force.
If you apply an external force, whatever the external force together with the weight divided by 3 will be the tension.
So the force will be down the force you apply. You don't really.
If the force you apply is downward, yes. If the external force you apply is downward, then if it's upward, then mg minus that applied force again will be 1/3 of t.
So if you put it down.
Yes, right, exactly. If you pull the string with another, the disk with another string, but with a less force, some less than some critical value, again it will go down. But in that case, the difference between the applied force and mg divided by 3 will be equal to t. This is always the case. Okay. So the question continue. Okay. In the second part, what is the magnitude of the acceleration of the center of mass of the disk in terms of g? And you will find this acceleration as 2g divided by t. But this is very easy. Just you will put all the values right in here. If you put I is equal to 1/2 mr square in the acceleration equation, you will find that the acceleration is equal to 2g divided by 3. Okay? Just in terms of g, the acceleration of the disk is 2/3 of g, and the next is just I'm showing this part explicitly, and you may just follow this. It's easy. Just put the value. So the next, what is the speed of the center of mass after the disk is descended through a distance h? In fact, this is nothing but the same type of question with the previous one. The rolling disk, after it has going a distance d, what was the center of mass, the velocity of the center of mass? It's the same thing. So we will follow the same type of equation. V square, V0 square, 2a times h. You already know what a is from the previous one. And initial velocity is 0 because you release from rest. And so the rest is just to calculate, to put a, the value of the a in the previous part, 2g divided by 3. And from this, you are able to solve v as 4gh divided by 3 squared. But you can solve this part by using the conservation of energy. And this is a nice review from the chapter of conservation of energy. Well, how can you solve this by applying the conservation of energy? You release the yo-yo from rest. It falls a distance h, but after it falls a distance h, its center of mass will have some velocity, right, v. But this is not the only motion of the disk. It is also rotating. And because of the rotation, it has also rotational kinematic energy, rotational kinematic energy, yes. Kinetic energy, sorry. Rotational kinetic energy. And this whole thing must be equal to potential energy, mgh, right? So if you formulate this in the perspective of the conservation of energy, this is the equation that you have to solve. But I guarantee you will find the same result with the previous one, because again, this omega and v are related to each other, right? Omega is nothing but v divided by r. So if you put this v divided by r, also if you put I, the moment of inertia, 1/2 mr square, right? Then you are one step away from solving v, and you can express v. Sorry. Just I leave it to you. Just if you put these values in here into this equation and solve for v, you will find the same expression in the previous case. So you find v both by using the conservation of energy and by using the kinematics of one-dimensional accelerated motion. So both ways will give you the same answer. Okay, normally our class ends here, but if you want, I can continue solving the problems. If you are tired, I can give a break and continue again after 10 minutes. So 1 p.m. Okay, so I can give you an extra lecture, whatever day you want. Tomorrow? Friday? Tomorrow 3 p.m. No, there is no lab.
You can take the time for extra class.
Or maybe you can have some time to work yourself this weekend and work on the last quiz. Also, last quiz will stop on Sunday, and next week I can give you another recitation hour, also including the some of the questions from your last quiz. I think this will be best, and before your final exam. So let's pick up a day next week it may be again the lecture hour on Tuesday or Thursday.
Tuesday.
Exam will be Tuesday.
Tuesday you have exam? Final? Thursday. So we can fix on Tuesday then. Tuesday on the same lecture hours, I will hold a recitation hour. Okay? At 1:30.
Hocam, salı günü çift sınav var ki.
Salı günü sınav var mı? Çarşamba da olur, fark etmez. Do you have any exam on Wednesday? You have? What time? What time? So pick up a time on Wednesday. Afternoon? Whatever afternoon. On 3 o'clock? Let's make it 2 o'clock, okay? Wednesday, 2 o'clock. Okay? So,